I'm assured by tonight's inaugural lecture that everybody that's meant to be here is here. So welcome to you all on behalf of the university to tonight's inaugural lecture. Is Informatics an Indiscrete Science by Professor Stephen Gilmore. Here are some that weren't invited, obviously sneaking in last. I'm Leslie Yellowlees, and I'm head of the College of Science and Engineering, and it's my very great pleasure to welcome you all here tonight. I really enjoy coming to these inaugural lectures, and I'm sure you will enjoy tonight's very much. It's had a lot of hype, so you've got to live up to that now, Stephen. Just a few biographical details is that Stephen is professor in the School of Informatics, where he has the chair of Software Systems Modelling. He studied computer science at Queen's University, Belfast, Northern Ireland, and after completing his PhD there, he moved to Edinburgh, where you've been ever since. Lucky us. So to take up a lectureship position and subsequently through the system to get his personal chair. And he's a member of the Laboratory for Foundations of Computer Science and the Centre for Systems Biology at Edinburgh. His principal areas of research is centred on the application of stochastic process algebras. I'm hoping we'll get a little more information about that later. That is the concise modelling languages for quantitative analysis of systems where concurrency plays an important role. And process algebras have a wide range of applications, and they can be used to predict the performance of computer systems, assess their scalability under increasing load, and detect flaws and insecurities in implementations. Get the teeth in, Leslie. Just a little extra information that was also supplied to me, that Stephen is a very dedicated family man and delighted to welcome his wife Jane and his two daughters Martha and Alice. You're all very welcome here today. But did you know that he enjoys playing Nintendo Wii with them all? Oh, yeah. And he's a champion in hula hooping. So, good hips, eh? Thank you. I'm also told that you have been known to rise before dawn to bake a cake. And I think that's going above and beyond the call of duty. So, I'll not ask if the cake was an unqualified success, although I'm sure it was. But here's a multi-talented man, and you're very privileged tonight to hear his inaugural lecture entitled, Is Informatics an Indiscrete Science? Stephen, over to you. Thank you very much.
Thank you. Well, thank you very much indeed, Leslie, for the introduction. Some of that is actually true as well. Well, it's a great pleasure and a privilege to be here speaking to you tonight. I've chosen as the title of my talk a question. And it's a question about the nature of the science of informatics, the science in which we're all involved in the lovely new building over the road. I chose this particular title for my talk because I, along with a number of other people recently, have been thinking a lot about Robin Milner and his wonderful contribution to the science of informatics. So in the School of Informatics this year, we held a memorial symposium for Robin Milner, which was a wonderful event and a wonderful chance to think about Robin's great contribution to computing and to informatics. And Robin posed this question in a lecture when he founded the institute that I'm in, the Laboratory for Foundations of Computer Science. He asked, is computing an experimental science? And he did a wonderful job of convincing us that, indeed, it is. And I thought it would be interesting, perhaps, to ask, well, what kind of experimental science is that? So what is the nature of computing? Is it the case that computers should only deal with discrete things, and it's a discrete subject? Or is it perhaps the case that we should sometimes use continuous science as well? Well, nowadays, of course, we speak about informatics rather than about computing. So the title that I've taken from my talk is the question, is informatics a science of the discrete or a science of the continuous? And in a way, this question seems to have a very simple answer. We all know the nature of computing. We all know that they're fundamentally concerned with discrete things. Ones, zeros, true and false. But I'd like to try to explain that perhaps things are a little bit more complicated than they might at first seem. Well, informatics is intrinsically concerned with modeling and abstraction of complex systems. So when we have a complex system and we want to try to understand it, then abstraction gives us leverage. Okay? It helps us to understand complex systems by simplifying them in the right way. Of course, it's important not to abstract too much. One should be not very pleased with an architect who came along with a model of your new building that perhaps looked a little bit like this. It's too abstract. We've missed out some important details here. It's hard to tell how many floors this building should have, and it's hard to tell which are the doors and which are the walls, and so forth. So this person has done too much abstraction. It's also possible to go wrong by doing too little abstraction. You could have a model of the system which is so complicated that it doesn't leave anything out, and then you haven't really done any modeling at all. It's as difficult to work with the model as it is to work with reality itself. So that hasn't given you any intellectual leverage. And what we seek is to try to find models which are precise enough without overcomplicating things. This is the art of modeling, to find the right level of abstraction to describe the problem at hand. Well, in informatics, the models that we work with don't look very much like pictures of buildings. They look instead rather like automata, such as this, for example. We might make a very simple model of a disk and say that it has a particular state, the working state, in which you can read data from the disk and write data to the disk. But of course, there could be an operation such as fail that moves the disk into a new state it's not been in before, the failed state. When you're in the failed state, you can no longer read and write information, until perhaps this failure is corrected by resetting the disk, and then you're back in the working state again. So an automaton like this is the kind of model that we sometimes work with in informatics. It's a very, very high-level model of a disk. Model of a real disk would be much more detailed than this, include more states and so on and so forth. But I hope this will give us something to speak about here at the start of the lecture. So informatics is also very concerned with languages. Natural languages, but also programming languages and modeling languages. And over the past 20 years, it's been my great pleasure to work on a language I'm very fond of, which is the PEPA process algebra. So PEPA is a language invented by my colleague Jane Hilston in her book, Compositional Approach to Performance Modeling. And PEPA, as Leslie told us, is a process algebra, a particular kind of modeling language. It's one that's geared towards performance evaluation of systems, hence the name, Performance Evaluation Process Algebra, PEPA. The book gives a semantics to PEPA in terms of mathematical structures called continuous time Markov chains. So all PEPA models are mapped to a continuous time Markov chain, and from this we can compute results telling us about the performance of the system, the utilization of components, the availability of components, the throughput, and so forth. So the underlying mathematical structure is a stochastic process, and it's a discrete state stochastic process. Process algebras also come with a wonderful tool called a bisimulation relation that allows you to tell when two models are equivalent. They're equivalent when each one simulates the other so closely that an external observer couldn't tell them apart. This is the notion of bisimulation. So if we had our high-level model of a disk and we tried to write it down in PEPA, it would look like this. It's a series of equations describing recursive processes, and this is a component in your system, and it has two local states, the working state and the failed state. While the disk is working, you can read and write data. When it's failed, it moves to the failed state, and when you're in the failed state, this failure must be corrected before you go back into the working state. So that description of the system in the PEPA language has the same content as the automaton that we saw before. Okay, we have the the transitions that we had before, we have the same underlying system in the following sense. There's an initial state which is special, the working state, and you explore the system by navigating from here. So you see all of the outgoing transitions from the working state that take you to new states. For example, the fail transition takes you to the failed state. And then you explore all the outgoing transitions from that state. The correct transition takes you back to the working state. And once you've explored every possible state that you can reach, you've evolved what's called the state space of the system. You've evolved a labeled transition system that describes the structure of the model. You know, everywhere it can get to, you've seen everywhere it can go. But the Pepper model also contains other information as well, because it's a timed process algebra. And there's a time associated with every activity in the model. So if we look at the model again, you see there are these rate variables written beside every activity. If we take those rate activities and we collect them up, then instead we get a different structure, which is the continuous time Markov chain underlying the model. So it's a finite state, stochastic process. Here it just has two states. And what we're concerned with is the transitions between states. So we can take that content in the Markov chain and turn it into yet another representation, which is a matrix. We're concerned with changes of state, so we notice that we can number the states. We can go from state 1 to state 2 at rate f. So we build a matrix, putting the value f in row 1 and column 2 of the matrix. We notice we can go from state 2 to state 1 at rate c. So in row 2, column 1 of the matrix, we put the value c. And this is the rate matrix underlying the Markov chain. And from this we can build yet another matrix called the generator matrix, by making sure that each row sums to 0. So we subtract from the diagonal the sum of all the off-diagonal elements. And that matrix, the generator matrix, is used in a very important equation called the global balance equation. It tells us the probability of being in the long run in the working state or the failed state. It's the solution to this equation, pi q equals 0. So we have pi w, the probability of being in the working state, pi f, the probability of being in the failed state, subject to the requirement that these numbers must indeed be a probability distribution. They have to add up to 1. There's something called the normalization condition. So taken together with the equations that we had before, the solution then is unique. We can uniquely find the probability of being in the working state and the failed state in the long run. For a simple system such as this, we can even find these solutions symbolically in terms of the rate variables c and f. And this is the solution. Okay, so we had a model of a system. We wrote it down in our favorite modeling language. We generated a labeled transition system, a Markov chain. We did some linear algebra, and we found the numbers that we were looking for. So that all worked out pretty well, and we didn't have any recourse to use a continuous state representation of the system. So at this point, probably we would be well placed to say, isn't informatics a discrete science? Why would we have any need of non-discrete representations of systems? So what's the problem? Well, the problem that arises is that we're not usually concerned with modeling just one disk. We're concerned with modeling systems, complex systems involving many components. So recently, Google published on their web page some pictures of their data center. Okay? So this is the problem. It's the problem of scale. It's the problem of scale. So what you're looking at here is an aisle in Google's data center. And along the sides of the aisles are servers piled high, one on top of the other. And this is one aisle. And we're in an enormous building, and there are many, many similar aisles. And these machines are running the services that we all use: mail and search and file sharing and Google Drive and so forth. So in the picture here, you have lights associated with every machine. And here, this is a good day, because the blue light means the machine is working. Okay? So the lights are all mostly blue. If you look closely, you find a very small number that are red. and that machine's not having a good day, so some engineer should come along and probably reboot that one or fix the problem or something. But this is the problem, that we're dealing with systems that we want to scale. We want to serve large numbers of clients, and hence, this is where the complexity comes in. So let's take a smaller example than that. Let's just take the previous system and replicate it so that we have just 6 copies of the disk. And now we do the same game that we did before. We start from the initial state, and we evolve all the states that we can get to from there. And this, surprisingly, starts to get you to a very large number of states very quickly. Each of these components can move independently of the others, and so you're coming to new states all the time. And you have to keep searching and searching through the state space to evolve each of these. So some of these states are similar to others in the sense that they're symmetric. But some are unique, and they occur only once. And you can be interested in finding the probability of being in one of these unique states. There's a particularly special one coming up just about now. It's this one, where all of the disks have failed. So you might like to know, what is the probability of being in that state of the system? So the difficulty that arises is simply that, the state space explosion, as we call it in informatics. So if we have one disk, we have 2 states. If we have 2 disks, we have 4 states. If we have 6 disks, as we did there, we have 64 states. If we have 10 disks, we have more than 1,000 states. If we have 20 disks, we have more than 1,000,000 states. And if we have 50, or 100, or 150, then the number of reachable states in the system is growing ferociously quickly. Okay? This explosive growth is the state space explosion. So that last number is certainly a very big number. But computers are used to dealing with very big numbers of things. Maybe we can just tough it out and see if things will just work. So that number at the bottom is 2 to the 150. And if you imagine that each of those states would need some memory to store a representation of it, then you could translate that into a number of bytes. You might translate it into 2 to the 152 bytes. Well, that's a number that factors as 2 to the 82 times 2 to the 70. And 2 to the 70 bytes has a name. It's something called a zettabyte. You don't hear people talking about zettabytes very often, do you? You've never heard anybody say they've just bought a 64 zettabyte phone. Why is that? How much storage is that really? Well, if you took all of the disks and all of the storage attached to all of the computers on this planet and put it together, you'd have less than 1 zettabyte. Okay. And we need 2 to the 82 times that. So that's not going to work. Even if we ask Google to help us, that's not going to work. And this is an old and familiar problem we encounter in a lot of contexts in computer science and informatics, the problem of state space explosion. We feel we've met an old and familiar foe here. We feel we've been there, we've done that, and we've even got the t-shirt. And this is the t-shirt. So the t-shirt says, "I love continuous time Markov chains." And it's a nice t-shirt. I can tell that you like this t-shirt. It's nice for the reason that it's good to be quantitative. It's good to be precise. Okay, these are all good qualities. The only problem with this t-shirt is that we wish it came in a larger size. So the next wonderful idea that Jane had was to take her previous semantics for Peppa and add a completely different one. Look at the problem in a completely different way. So we start with exactly the same recursive process definition that we had previously, and now say, we're not concerned about finding all of the reachable states, because we know we can't go very far down that route. So what we're concerned with now is just estimating the number of disks in particular states. So the number of disks which are working and the number of disks which have failed. So we have some constant population of disks, some number like 150, and some of our 150 disks will be working and some will be failed. Well, if that's the case, then we can compute the rate at which working disks turn into failed disks. It depends on the rate at which one disk fails and the number of disks which are working. And we can compute the rate at which failures are corrected. Failed disks turn into working disks. So it depends on the rate at which you can fix one disk and the number of disks which have failed. So this is a completely different model of the system. It's called a fluid flow model. So you have two variables now estimating the number of disks in the working state and the failed state, and you have flow between these two, from working to failed. And from that, you can make a different mathematical representation of the system. And the different mathematical representation is a system of ordinary differential equations. We can write down the rate at which working disks become failed disks, the rate of change of W with respect to time t. So dW by dt. So you put a negative term in the differential equation because every failure from W's point of view is a loss. There are fewer disks working. And you put a positive term in the differential equation because every time a failure is corrected, that's a win. From F's point of view, everything is completely the other way around. Every time a failure occurs, that increases the number of failed disks, and every time a failure is corrected, that's a loss. So that puts a negative term in the differential equation. So once you have this representation of the model, the fluid flow representation, you can start to compute with it. One thing you can do is you can solve the initial value problem, which is to say you set up the number of disks initially which are working and which are failed, and then run the differential equations forward to generate a trace showing you how these numbers change as a function of time. You can also solve this system to find the stationary point to the differential equations, which occur when nothing is changing. So we put zeros down the left-hand side, and we solve and we find we have these straight lines. And these straight lines will continue from this time onwards and onwards and onwards forever. We can rearrange those equations to find the value for the number of working disks and the number of failed disks in terms of the population, n, and the rates at which failures occur and failures are corrected. And these are those solutions. So now we have a totally different way of looking at our model that avoids the state space explosion problem. But we've got two alternative semantics for our system. Well, if you wake a semanticist from a deep sleep and tell him you have two semantics for your language, that person's going to ask you the question, are these the same? Or in what sense are they the same? And do they agree? So how are we going to decide that? Well, how are we going to compare them? Well, the problem is, of course, we can't solve the Markov chain. That's the very large number of states, the zettabytes, more storage than on all the disks on the planet, and so on. So we can't solve the Markov chain, but we can simulate the system. So we can make a Markov chain simulation of the system, starting from the same initial values and simulating forwards. The number of disks working and failed goes up and goes down as failures happen and as failures are corrected. So such a simulation run is informative, but it's not definitive, in the sense that if you want to know these long-run values, you can't tell it from one simulation run like this. How do we know this? Well, if you perform another simulation run, a discrete event simulation with pseudo-random number generation, you get a different graph. If you perform a third run, a different graph again, and a fourth run, a different graph again. And none of these definitively tells you what is the long-run value of the number of working disks and the number of failed disks. So the thing to do is to start taking averages over multiple runs. We can take the average over 10 runs, or 100, or 1,000, or even 10,000. And once we take the average of 10,000 simulation runs, we get a very familiar graph. We get this one, which is predicting the average trajectory taken by this system. So this is the average of 10,000 simulation runs, and this is the solution of the differential equations. Okay? So we can perform 10,000 simulations, or we can generate and solve the differential equations. And since generating and solving the differential equations takes less time than doing one simulation run, well, that's an absolute no-brainer. Okay? We'll generate and solve the differential equations. So now I've got a new t-shirt. Okay? It says, I love ordinary differential equations. Again, it's a very nice t-shirt. I think you'll agree with me. It's nice because it's quantitative and it's precise. But the particularly nice thing about this t-shirt is it comes in this extra large size. So now we can scale our analysis to solve the large-scale problems that are of interest to us. So Pepper is a very unusual language in having these two alternative semantic descriptions, the discrete semantics and the continuous semantics. Most modeling languages do not have two semantics in this way. Now, the previous example, I hope, convinced you that this method would at least work for us, but for a very small and rather simple artificial example. And just because something works on a small example doesn't necessarily mean it's going to work on a larger, more complicated one. So let's try a slightly larger, more complicated one, the kind of systems that we model in Pepper. So this is a system containing components of different kinds, making up a secure web service. So the web service is made up of a number of threads running on a server. It's inside a protected area behind a firewall. And first-party clients can connect to the web service directly. They're trusted and they're on the local intranet. So they can connect to the web service directly. Second-party clients are outside on the internet, and they connect to the web service through a broker, an intermediary. This broker might connect them with a number of different web services, the way a price comparison website would. So Trivago or Skyscanner or something else. Contact a number of different web services on your behalf. And each component in the system is replicated. There are many second-party clients, there are many brokers, there are many threads running an instance of the web service, and there are many first-party clients inside the firewall. So this system is going to work by using encryption to secure the communication. So the second-party clients have to spend some of their lifetime encrypting messages, making requests to the broker, receiving a response from the broker, and then decrypting that. The broker waits for a request from the client, decrypts it, re-encrypts it for the web service, makes a request to the web service, waits for the response, decrypts the response from the web service, re-encrypts it for the second-party client, and gives back the response. The first-party clients inside the firewall don't need to do any of this encryption at all. They're trusted, and so they can simply invoke the web service by a remote method invocation. And the web service divides its time between listening to requests coming in from the inside and from the outside. So from the outside, the broker is sending requests, routing requests from the second-party clients. And from the inside, we have these invocations coming from the first-party clients, and that's the web service. So a Pepper model of this system puts together a number of copies of these components. There are second-party clients, which speak to brokers. There are first-party clients, which speak to the web service. And there's a composition between these so that the brokers also speak to the web service. So this is the model we'd like to look at. So I think it's not an entirely trivial model. It doesn't have obvious symmetries that you could exploit to simplify the problem. Okay, so we'd like to look at this as the number of copies of each of these four components increases. So this is the smallest possible instance of the system, just one of each kind of component. But let's see how the various analyses that we have available to us fare as we start to scale up the model. So if we have just one copy of each component, we have a very small system There are only 48 states in the reachable state space, and even if we apply methods like symmetry exploitation, we can't reduce this any. These are 48 good states in the state space. We could solve this using a sparse matrix representation and find the steady state solution of the Markov chain. We could use a cleverer data structure called a multi-terminal BDD, a binary decision diagram. We could again find the steady state that way. We could perform a transient solution, see all the probabilities up to a particular stop time, like t equals 100. We could perform a Monte Carlo Markov chain simulation, or we could generate and solve the ordinary differential equations. And each of these kinds of analysis for this very small and simple system costs you basically nothing at all, just a couple of seconds of computation on a regular laptop. But let's scale things up a little bit. Suppose now we have 2 copies of each of our components. Well, suddenly we find we have 6,000 states, but we can exploit symmetries and reduce this down to merely 800. And again, we can solve to find all of the results that we want in just a few seconds, right across the board. So we scale up a little more. Suppose we have now 3 copies of each of these kinds of components. Well, suddenly we find we have more than 1 million states in the state space. And even if we aggregate that and exploit symmetries to reduce states which are similar, we still have more than 160,000 states. And now suddenly the state space-based methods are starting to struggle. They're starting to take minutes rather than seconds to compute answers. So 10 minutes to compute the transient solution of the Markov chain. Well, still, 10 minutes is not too bad. Perhaps we're not in very much of a hurry. But the problem is that we can't go very much further than this at all. If we had only 4 copies of each of the components here, we would have more than 230 million states, and the discrete state approach, trying to enumerate all the states, simply is going to run out of memory. So all of these methods will cease to produce results for you, and then you're left with using those methods that don't involve generating the state space, such as performing a simulation, or many simulations, or generating and solving the differential equations. But these methods will continue to scale well beyond the limit of the state space-based methods. And further, the very good news is that these kinds of analysis give you detailed and informative results. They tell you the number of copies of each of the components that you have in each of their local states as a function of time throughout the entire time course of interest. So we can find this for the second-party clients, for the broker, for the first-party clients, and for the web service. So it's generating detailed results and giving them back to us for what I think is a non-trivial modeling problem. So this has been an example where discrete methods have failed and continuous methods have succeeded. So is it possible that we've got it wrong all the way, and informatics is instead a continuous science? We should be using continuous methods all the time. Well, I don't think that's the case, and I wouldn't try to convince you of that. And here's an example where using continuous methods alone didn't entirely work out well. It's from a different domain. This is a modeling problem in biology, the modeling of the MAP kinase cascade. So this is a signaling pathway that's involved in the response to stress stimuli, such as oxidative stress, DNA damage, or infection, and so forth. Okay? So such a pathway is a series of chemical reactions, combining chemical species to form compounds, and some of these reactions can be reversible, so they break up again. You get different parts of the compound out. They recombine in other ways, and so on, down through the cascade until eventually we reach the bottom. And that's the signaling process at work in all living organisms. So we looked at a model of this cascade published by Schobel et al. In Nature Biotechnology. We thought it'd be interesting to see if the PEPA language could reproduce the results of a particular study that was already published and authoritative and very well done. So we took the Sherbel example as our test for Peppa's new continuous space semantics. So it's quite a complex model. It's been very influential. It has more than 700 citations, which is a great citation count for a paper that's 10 years old. So it's been a very successful paper. It's a very detailed and worthwhile computational study of the problem. The differential equation model is non-trivial. It has 94 reagent species and 95 parameters. So it's a large and complex model. A great thing that biologists do is when they publish their models, they also publish supplementary information, in which case they publish the program that they use to compute the results in the paper. So this is great for other people interested in the problem. They can get the program, work with it, they can do their own investigations, try and reproduce the results and learn in that way. It's a very good tradition. So Sherbel et al. Had published their computational model as well. It's in the form of a system of differential equations coded in MATLAB for the MATLAB programming language. So we were able to start from this MATLAB model and the network diagram that you saw previously. And Adam Jugud was able to build a Peppa model of this, looking at the graphical representation and the MATLAB model and coding this up in Peppa. So when he did that, he fed his Peppa model into his analysis tool, Choreographer, and this generated a MATLAB model for him, an ODE model from the Peppa model using Jane's fluid flow semantics. So then that MATLAB model looked very different from the hand-coded model, as you might expect. But he was able to evaluate them both with exactly the same numerical integrator in MATLAB, which he set up in exactly the same way. So the same options for the integrator, the step size, the relative tolerance, and so forth, made sure he set all the parameters of the integrator the same, ran both models, and compared the results. And doing this, he was able to reproduce the results of the published model, which is great. So that was a success, but it was a success in reproducing already known results. But because Peppa is a high-level language and it has two semantic accounts, he was also able to perform a discrete analysis, a simulation, using Gillespie's tau-leap algorithm. So then this is a way of comparing the model against another way of interpreting it that wasn't available to the biologists. So what happened when he did that? So it turned out that the results did not agree, and they differed widely. So for example here, the published model in the paper, in Sherbel's paper, predicts a peak for a particular chemical species, RAF GTP, at 8,000 molecules. Whereas the Peppa simulation predicts a much higher peak at 16,000 molecules. And these numbers are not close to one another. So there's a discrepancy here. So it's likely that one of these is right, but at this point we had no idea which was the right one. So we thought, well, our results are computed using our simulator. Perhaps some bug in the simulator is giving these wrong results. So we had a little look at the code, but couldn't find the bug there, and it was producing correct results for other models. So we took a little close look at the results from the ODE model. In particular, the passage of interest is right at the start of the simulation here. It's the first 10 minutes. That's where all of the activity happens. After that, it's essentially straight lines. So let's zoom into the first 10 minutes. And then you have this graph. So two things come from this graph. You can see more clearly the difference between the two peaks. But also, one notices that the solution from the ODE model looks a little bit strange. It doesn't in particular look like a continuous smooth curve. And it does something very odd. it hits its maximum value right at the place predicted by the simulation at 2 minutes. And that crossing point there from the differential equations, it hits the simulation trajectory exactly, which is a little bit surprising. And it also hits it exactly at 4 minutes. That's also a little bit surprising. So what was happening here was that the parameters to tune the numerical integrator had been set to have a large step size of 2 minutes. And in so doing, the results computed step right over the true peak and onto the negative gradient. So they miss the true peak entirely, and then they go down from there. So they don't find the true trajectory of this molecular species. So we went back to Scherbel's model, and we adjusted this parameter, the very large step size, to make it smaller, and then re-evaluated their model. And when you do that, you have this graph. So the old trajectory is now printed in red, and there are two lines, a blue line and a green line, that are lying exactly on top of one another. So the solution from the differential equations is now computing exactly the same trajectory as the simulation. Okay? So the problem was not setting this parameter correctly in order to configure the numerical integrator. So it's a problem that comes up with continuous methods and not with the discrete method that we were using. Now, the moral of this story is not that someone made a small mistake in computing the results from a very complicated and worthwhile model. That's not the point here. The point is how this mistake was found. It was found because, well, we have a high-level language, and there are different ways to interpret models in this language. And having two ways to interpret the model allowed us to see this discrepancy between the computed results and what the true results should be. So it's really a success for high-level languages. So this was a case where the other case where continuous methods failed us a little bit and discrete methods succeeded. So I think it would be nice if informatics could be both discrete and continuous. And my favorite example of why this should be the case comes from Nigel Thomas. So Nigel is a long-time supporter of PEPA and a very valuable member of the PEPA community. And he made a model of a key distribution center. So a key distribution center allows principals to set up a secure session for them to communicate privately, like FaceTime or Skype and so forth. So you want to make a connection to someone else and chat privately, and you need a trusted third party to do this. So you previously register with the third party, and then you contact them before contacting the person you'd like to speak to. There's a protocol which is often used in these systems called the Needham-Schroeder-Lowe protocol. It's a very famous protocol in computer science. And it works something like this. For some reason, I've called my two principals John and Edward, for a reason that will become clear momentarily. So John sends a message to Edward saying that he'd like to request a session with him. He'd like to chat to him. And he first contacts the server. And the server generates for him a new key, encrypted under John's registered key. So only John can read the contents of this key. These new keys that are created all the time in secure systems are like passwords. You should change them periodically to make sure that no one knows them. No one can copy your messages. So this session key is encrypted for John, and there's another copy that's encrypted for Edward. So John sends the copy on to Edward, and Edward can decrypt that. Edward replies with a random number, a number that should only be used once, called a nonce. And this is encrypted for John under the session key. John decrypts that, makes a small change to the number, and sends it back to Edward. Right after this mysterious process completes, John is convinced that he's speaking to Edward. This is a fresh session, not a replay of one that occurred earlier, and everyone is well authenticated. So a PEPA model of this system looks like this. You first make a model of the key distribution center that accepts requests and gives responses. You make a model of John's behaviour. He makes the request to the key distribution centre, gets the response, then contacts Edward, who replies to John. Then they confirm this by updating this special value, the number, the nonce. Then they can participate in their session, their secure session. Edward's lifetime is a little bit simpler. Doesn't have to contact the key distribution centre, but otherwise proceeds in the way previously described. And the system that we have here has the key distribution centre speaking to a number of Johns and Edwards, so a number of senders and receivers. This is a slightly different model from the kind that we've seen previously. It's not that we have sequential components which are replicated. What we have replicated is a composition of sequential components, and that's a different thing. So that then is not in the correct form to apply the fluid flow semantics, the profitable semantics that scales well for us. So then we'd be in the world of continuous time Markov chains, and you know what happens there. State spaces and exponential growth and so forth. So we'd be in big trouble. So we need some way to solve this problem. So what's the way to solve this problem? Well, there's absolutely nothing wrong with the Markovian semantics. It's tremendously useful for small scale problems. But what we have in the center of this problem is a small scale problem. We have one John and one Edward. And what we can do is we can combine them into a single behavior that we could call Jedward, for example. So Jedward is John and Edward. It's an absolute replacement for John and Edward. And it's an absolute replacement in the sense that it's bisimilar to the composition of those processes. Technically bisimilar. But where would we get such a process from? Well, fortunately, there's a fantastic trick that allows us to do this, which is due to Nigel Thomas. I started calling it partial evaluation, but it's definitely Nigel's idea. And Nigel's idea is the following. You use the Markovian semantics to generate the label transition system and the Markov chain representation underlying these two components, John and Edward. Well, then you've got a Markov chain. But every Markov chain is isomorphic to a sequential Peppa process. So you can just take that Markov chain and push it backwards through the semantics and end up with a Peppa process, the one whose image under the semantics is the Markov chain you're holding in your hand. Okay? So that's what the Jedward process is. It's essentially a Markov chain, where we've labeled the states. Now the question is, would the results we're computing be disrupted by this interference with the model? Will it have altered the results? That would definitely be a bad thing. Fortunately, the answer to that is very clearly no. It won't have changed the results that are computed. Again, this is a theorem that's proved in Jane's thesis, that Peppa is a compositional modeling language. So you can take components out, you can replace them with bisimilar ones, and the results that you compute will be the same. So by making this change, we won't affect the results that we're computing, but we will be able to apply the profitable fluid flow ordinary differential equation analysis. So the model now looks like this. The key distribution center is as before. In place of John and Edward, we now have Jedward, and our system description contains the key distribution center and a number of copies of Jedward. Shudder. Okay, many Jedwards. Okay, but that's in the right form to apply the fluid flow semantics. So it's a nice ending to the story, and you can get there because you have both a discrete Markovian semantics and a fluid flow semantics. Use the discrete Markovian semantics to manipulate the model in order to later be able to use the fluid flow semantics. So in this talk we saw some small-scale models. And for small-scale models, Markovian modeling works beautifully. You can compute the results you want. You do a thorough stochastic treatment of a discrete state process. We saw some slightly larger ones as well. And for larger ones, there were good algorithms and good data structures that allowed us to tolerate largeness. And of course, we could always perform simulation to investigate a slightly larger model. And for the very largest models, these very large-scale models, we could switch to the continuous representation. We could use the fluid flow semantics to allow us to explore the behavior of the very large models that we encounter. So it seemed from all of the above that discrete or continuous methods alone just won't cut it right across informatics. And it should surely then be the case that informatics is not a discrete science. It's not a continuous science either. It's something else again, which we could call an indiscrete science. Well, I'd like to close by thanking all the wonderful people in the PEPA community that it's been my pleasure to work with down through the years. So on this slide are the people who did the wonderful theory, the mathematics underlying PEPA. They made the definitions, they proved the theorems, they compared the semantics, they wrote the semantics, they defined the equivalence relations, and so forth. So these guys are the composers who made the music. On this slide, these people are the people who've applied PEPA down through the years. Their interest was in a particular modeling problem, or they were stakeholders in a particular kind of system, and they wanted to really understand that system, to model it and to work with it. And so because of their interest in these things, I think this really deepens the value of the theory work that's been done. So these guys were the musicians who played the music. And there's a special place in my heart for the people on this list. So the people on this list are the implementers who implemented the software tools that allowed people to do the modeling. And they made a kind of a bridge between the theory and practice. And there's a lot of work that goes into software implementations, and we have had some wonderful people working on tools for PEPA down through the years. These guys are the instrument builders, right? They build the instruments that the music is played on. So thank you to all of them. And in preparing this talk, it's been a wonderful opportunity to look back on the PEPA community and to think about these things. And I came away with a lot of very happy memories of the time that we've spent working with PEPA. So chiefly among those are graduations. It's a lovely time when students graduate and they've done all this good work and they graduate, and various meetings that we've been through down through the years and various nice things that happened. And in particular, the time that Michael Smith came to the Pasta workshop and brought along an electric guitar. And he sang a song about PEPA. I mean, you just can't see that coming. So thank you to all of the above named people, and thank you very much for your attention.
This production is brought to you by the University of Edinburgh.